Alright, welcome to another video for chemistry. In this video we're going to continue our discussion of stoichiometry. So this is a problem dealing with glucose. Okay, so this is a stoichiometry video part 2. So here's our problem. So the food that we eat is degraded or broken down in our bodies to provide energy for growth and function. A general overall equation for this very complex process represents the degradation of glucose to carbon dioxide and water. So chemistry students, this equation should look very familiar to you because this is the one that we looked at great detail in biology when we talked about cellular respiration. So this is the breakdown of glucose in the body with using oxygen. Okay? All right. So here's our problem. If 856 grams of glucose is consumed by a person over a certain period, what is the mass of CO2 that is produced? Right? So we have 856 grams of glucose. That is our beginning point. That is our given, and we want to turn that into mass of CO2, which means we want to go from grams of glucose to grams of CO2. But there's a problem first. Before we get started, we always want to make sure, because this is stoichiometry, and if you remember from the previous video, stoichiometry involves the coefficients of a chemical equation. We always want to make sure to look to see if that chemical equation is balanced. This one is not balanced. So going back to the previous videos, okay, a good rule of thumb when trying to balance out equations that I told you before is to locate the most complex molecule in this equation. Okay, it's fairly obvious that glucose is the most complex molecule. So let's go ahead and start off with 1. Okay, so if we start off with 1 mole of glucose, okay, for every 1 mole of glucose we have 6 carbons. So that means I need to go over to the product side and I need to locate carbon. Now carbon has CO2, or CO2 has carbon, and I need 6 carbon molecules, or I need 6 carbon atoms in that. So that means I need 6 CO2 molecules. 6 CO2 molecules will give me 6 carbons, which will balance out with the 6 carbons I have in glucose. All right? Now you'll notice that there's oxygen there, but let's ignore oxygen for now. Let's move on to the next element in glucose, which is hydrogen. Okay? Now you'll notice that on the reactant side, okay, I have, with 1 mole of glucose, I have 12 hydrogen atoms. Okay? 12 hydrogen atoms, which means on the product side I need to have 12 hydrogen atoms. And I have a water molecule there which has 2 hydrogen atoms per water molecule. That means my coefficient needs to be 6, right? Because 6 water molecules will give me 12 hydrogen atoms. Okay? So my carbons are balanced, my hydrogens are balanced. Now my oxygens need to be balanced. You'll notice on the reactant side I have 6 oxygen atoms on the product, on the reactant side. So on the left there where it says product, that should say reactant side. So I'll make sure and fix that when I edit it. Now on the product side I have 18 oxygen atoms. So I have 18 on the product side, but I have 6, and those 6 come from the 1 mole of glucose. So I need 12 more. I need 12 more atoms of oxygen to balance out this entire chemical equation. So oxygen is a diatomic molecule, so it comes as O2, and so for every oxygen molecule I have 2 oxygens, so that means I need how many? 6. Good. Alright, well, I'm balanced. So now I have a balanced chemical formula which I can go back and reference to when I need to. Because look, I'm going from grams of glucose to grams of CO2, which means I'm going to need stoichiometry. I'm going to need the coefficients in my chemical formula. Alright, well, let's first start off with my given. My given was 856 grams of glucose. I need to convert that grams of glucose into moles of glucose, because moles is where my ticket is to get from glucose to carbon dioxide. So previously I looked up my molar mass of glucose. So that's the molar mass of carbon times 6, molar mass of hydrogen times 12, molar mass of oxygen times 6. If you need a refresher on how to find molar mass, please see previous videos. Okay, so the molar mass of glucose is 108.2 grams per mole. So for 1 mole of glucose, I have 180.2 grams of glucose. Now what that's going to do is that's going to allow me to get rid of that unit of grams and convert it now into moles, right? So essentially that's 856 divided by 180.2. And that gives me 4.750 moles of glucose. All right, now I'm in moles. Now I can actually reference, I can now go to, I can use my chemical equation because I have moles of glucose, but I want to get to mass of carbon dioxide, which means I need a conversion factor that will get me from glucose to carbon dioxide, and there is a conversion that does that, and that is in my chemical equation. So I need to find the relationship between glucose and CO2, and so for every 1 glucose molecule, I produce 6 moles of carbon dioxide. So there's my ratio, okay? And seeing that I want to get rid of moles of glucose, I want to make sure that the mole of glucose is on the denominator end and then the mole of carbon dioxide is on the numerator end, right? So that'll help me get rid of that unit, and that'll help me to convert 2 moles of CO2. And now I just performed the math, which is 4.75 times 6. That gets me 28.5 moles of CO2. Now, I'm finally at CO2, but there's a problem. I'm in moles of CO2. I need to convert moles to grams, right? I need to go to mass. Well, what's my unit? What's my conversion factor that I can use to go from moles to grams? Well, that's my molar mass. So for 1 mole of carbon dioxide, my molar mass will be 44.01, right? So that's my carbon moles, my carbon molar mass, plus my oxygen molar mass times 2, because there's 2 oxygen elements in carbon dioxide, and it all adds up to 44.01 times 28.50. My moles unit cancels out, and my math gives me 1,250 grams of CO2, or in scientific notation, 1.25 times 10 to the third grams of CO2. So 185 grams of glucose, when I consume that and my body burns that up through the Krebs cycle, the ETC, all that good stuff we learned in biology. Remember, CO2 is a waste product of this process of producing ATP. So 856 grams of glucose will produce 1,250 grams of carbon dioxide. Okay, so again, this is another example of how stoichiometry helps us. It gives us a connection, if you will, from one element or one element to a compound or vice versa. Okay, so it's very essential, especially when I get into the mole stages. So in this case, I had grams, which was my given. I need to convert that to moles because in the moles unit, that's where I find my conversion factors. That's where the stoichiometry really, where the rubber meets the road, where I can find the units, my conversion factors that will convert from one compound to another. So I went into moles of CO2 from moles of glucose, and since my problem was asking me for grams, I can just simply use my molar mass ratios, and I got grams of CO2. Okay, so that was that's an overview of the process that I just went through to convert grams of glucose to grams of CO2. All right, that concludes our stoichiometry problem for glucose, and on to the next one. Good luck in your studying.